And what we're working on at the moment is try and get a more detailed picture of the full set of signatures of this and Piyush Kumar will talk about that, or aspects of that, on Thursday. To comment, typically this signal will, the first thing I want to say, is we have light neutrinos, is that telephone, if it stays on long enough, and the LHC for sure will detect these neutrinos. But more important for string theory is, can we distinguish these vacua from other vacua? So the idea is to try and get in different corners of the landscape a good idea of the collider signature of the different corners and compare them and distinguish them. Then we can use the data to say, yeah, we could live in a heterotic vacuum, or we can't live in a type 2B vacuum, or we could live in a G2 vacuum. It's not, it's a very basic idea. Okay, so that finishes the sort of part on LHC and M theory. I'll just finish with a couple of comments on some more recent work that we've been doing in Fiesta with Roberto Valandro, who's here and is actually graduating, so he's applying this year, and Francesco Benini, who's a younger student, and Roberto's giving a short presentation on Thursday on some of this stuff. So in five-dimensional warp models, the basic picture that's emerged is like this. You have an ADS5 bulk, a UV brain, an infrared brain, and standard model fields in the bulk. Now to get zero mode, four-dimensional zero mode, these fields in the bulk require bulk 5D masses, and depending on their spins, boundary masses as well. And these things have to be sort of tuned and in order to make all this, this picture work. At the end of the day, you get a picture where the electrons are localized in the UV, heavier objects are localized, heavier particles are localized in the infrared. So the question we were interested in addressing is, how does string theory, how can we actually understand that picture from a microscopic point of view, and how does it change and so on? So since you need the standard model fields in the bulk, the only place where we have warp factors, or if I understand, a spectrum of warp factors, if you like, is in the type 2B context. And there the question is, what type of brain, on what type of brain we put the standard model field. So it has to be rat brain. And in this case, we were studying D7 brain. And then the question is, how do you get, masses in particular in those 5D warp models? You have to put in 3 generations of fields, all with bulk masses. But the only way that we know how to replicate gauge quantum numbers from a microscopic point of view is through topology. For instance, one can get different numbers of fermion zero mode in topologically non-trivial backgrounds. So the way we do it is by, so this is a stringy picture of the warp compactification. the 7 brains are mapping a 4 cycle, which has one direction, which is being warped, 1 volt direction. And to get replication, one can switch on gauge instantons on the 4 cycle. So ordinary instantons, which are these things, remember they have a scale, and these are actually flattened out D3 brains inside the 7 brains, parallel to the 7 brains, say. And we actually get a new mechanism for localizing the fermion wave function, because they're localized both by instanton and the warp factor. And even though I won't attempt to give an overview of the results, the basic picture is that Yukawa couplings can be both suppressed and enhanced by the warp factor, as in the 5D models, but also the instanton scale size and in those formulas. But Roberto will say a bit more about that in his short presentation. So, let me just conclude. We've seen that M-series Type 2B vacua can have both a hierarchy and moduli stabilization, and we can actually understand it quite rigorously. Using this, it's possible to confront collider data